Hello, and this is Group 10's project for a software-defined networking-based intrusion detection system with automated DDoS mitigation. So our project contains four main components. The first is the front end built with React, and this has all of our traffic controls, host statistics, IDS alerts, and mitigation flow visibility. Additionally, we have a fast API interface, which acts as a API gateway for our Ryu IDS controller and our mininet with Open vSwitch topology. So going over to our system architecture diagram, as you can see, our orchestration layer, which is a fast API backend, actually controls two separate things. The first is our Mininet's iPerf generator, which lets the fast API backend generate random traffic throughout our system. And next we have our Ryu REST interface, which lets us query for traffic monitoring statistics, IDS detection alerts, as well as mitigation logic. So the reason we have these two systems separate is because if we want to, say, simulate a targeted attack from one host to another, we would do so through the Mininet iPerf traffic generation, and this would be completely separate from our Ryu controller. So our Mininet iPerf generator would know which host is attacking another host, but our Ryu controller will not know that, and instead will have to detect the attack and mitigate it itself. So let's go ahead and start up our project. First, we want to initialize our Mininet topology. Then we're going to start up our Ryu controller, and then our fast API gateway and our front end. So going over to our front end here, we have a view for our network topology and how it's arranged. We have a table for our host statistics, IDS alerts. We have a control panel for our controls that lets us start attacks or simulate traffic. We have a chart for traffic throughput throughout our network. And finally, we have evaluation metrics here, as well as what OpenFlow rules and meters get installed on our network. So let's first start off by showcasing our normal traffic scenario. So in this situation, we would generate random traffic amongst all of our hosts. So all hosts are sending traffic and all hosts are also receiving traffic. And as you can see here, our network is pretty stable and our host statistics shows the throughput of the bytes passing through each of them. And if we take a look at our Ryu controller, we can also see that every half second we are getting or requesting data about the flows, the status, the meters, and the stats that are coming from the Ryu controller itself. So that's how we populate this information right here. So let's start by going over a single source flood. In a single source flood attack for our system, our backend will randomly select one host to be the attacker and another host to be the victim. Of course, since this is separate from our Ryu controller, the Ryu controller has no idea which host is going to be the attacker and which one is the victim. Its job is just to detect which one is the attacker and install a drop rule on it to block all incoming traffic to the victim from the attacking host. So let's see what happens when we start a single source flood. So it happened really fast, but as you can see, H2 is the attacker and H5 is the victim. However, the system blocked or it implemented a rule to block traffic coming from host 2 to host 5. Now let's take a look at what happened on our chart. So as we can see, when we started our attack, the packet rate skyrocketed for our victim before dropping. And now the packet rate throughout our network coming from the attacking host is still relatively high, but our victim is completely blocked from it. And if we look at our OpenFlow rules that get installed, we can see that there is a drop rule that got implemented from host 2 to host 5. And looking at our evaluation metrics, our system took 824 milliseconds to detect it and 0.3 milliseconds to install the drop rule. So the throughput went from 215 megabytes per second to nearly zero. So now let's talk about a multi-source flood attack. In a multi-source flood attack, our system will randomly select three hosts to be the attacking hosts in this situation and one to be the victim again. Now, since we have multiple hosts targeting one victim, this is known as a DDoS attack. And instead of just installing a flow rule to drop packets coming from attackers, we are instead going to rate limit the attackers using open flow meters instead. So let's go ahead and demonstrate what that will look like. So as you can see, hosts H3, 4, and 5 are the attackers, and H2 is the victim, and now it's under attack, but these hosts are now being rate limited. So let's pause our chart, and as you can see here, throughput of our victim is through the roof. However, you can see this dip means the rate limits have been installed, and now our victim's throughput is relatively low. So as you can see here, our open flow rules installed 3 rate limiting rules on the 3 attacking hosts. And if we go down to our open flow meters here, we can see that we had 3 meters implemented on the 3 attackers. So if we go to our evaluation metrics, we can see that it took 711 milliseconds to detect the DDoS attack, 0.6 milliseconds to install the rate limiting rules, and our throughput dropped tremendously afterwards.